Testing, testing.
Good morning, everybody. Welcome to the Off Track. This morning, I would like to introduce Gia, who is talking about primitives for security audits, lessons from Jakarta Mail. Thanks very much.
Thank you. Testing. Right. Good morning, everyone. I hope you are having a wonderful morning today. Thank you for taking the time to attend my talk. It's my second time speaking at a conference, and I hope that by the end you have some takeaways from this sharing. My name is Jia. That's me over there with a very friendly red-tailed black cockatoo. I'm currently a consultant at Altum, where we help our clients secure their assets through pen testing and other services. On the side, I'm also interested in web security research during my spare time. So, question for everyone before we get started is, when was the last time that you look into how various libraries are actually implemented? So, there are plenty of informative talks these days about identifying vulnerabilities that follow certain bug patterns. They can be very useful when learning about the different vulnerabilities. However, hardened targets are less likely to have this sort of crackable bugs. At some point, it is going to be useful to audit libraries in order to identify primitives that can potentially be misused. So primitives are not actually like bugs per se, it's more like features. So that will be the main aim of this sharing today, using a case study around Jakarta Mail as an example. We'll first look at the background of Jakarta Mail, followed by a short primer on encoded email strings. Then I'll be sharing various primitives I found in Jakarta Mail, namely the internet address and my message classes. Similarly, primitives in Spring Framework will also be shared, and then we will end with the email annotation from Hibernate Validator. So, what exactly is Jakarta Mail and why is it not called Java Mail? Well, the Java Enterprise Edition name can be confusing, especially when we see that Java 2 was renamed to Java and then losing the word Java altogether. So, Java 2 Enterprise Edition, or J2EE, was released in 1999. This saw the introduction of specifications relating to enterprise technologies such as enterprise Java beans, Java server pages, Java naming and directory interfaces, which we recognize as JNDI. In 2006, J2EE was renamed to shake off the number 2, and Java Enterprise Edition 5 was released. We see big changes such as the introduction of annotations. Finally, in 2019 and beyond, Java EE was renamed to Jakarta Enterprise Edition, after being handed over to the Eclipse Foundation, as Oracle still owns the trademark to the name Java. If you are curious, there's a lot of backstory regarding the change of ownership from Sun Microsystems to Oracle and finally to Eclipse, where development is currently at. So this is just a simplified timeline, and today the latest version is Jakarta EE 11, with version 12 in the works. So where does Jakarta Mail reside within the Jakarta EE platform? Think of the platform as a container that contains a bunch of different modules. Within this container, there are smaller containers known as profiles, which comprises of a subset of Java components. So developers looking to create a compliant framework will just basically have to refer to this list. And some of the frameworks that we may be familiar with are Apache Tom EE, IBM WebSphere, or Eclipse Glassfish. So the component that we are looking at today is Jakarta Mail, and it is part of the broader Jakarta EE platform. During my research, I looked into Jakarta Mail version 2.1, which is the latest version released since Jakarta EE 10. According to their website, 2.2 will be released for Jakarta 12. Looking at the Jakarta Mail page, we can see that there's only one known implementation, which is Angus Mail. With that, we now know what Jakarta EE and Jakarta Mail are. Okay, let's sidetrack for a bit for a very quick primer on encoded strings in email addresses. This is original. I want to give a shout out to Gareth from Portsfigure, who published a very detailed write-up on potential misuses with encoded strings in email addresses. So if you haven't already done so, please take a look at his write-up and presentation. It's super interesting. So in my experience during my research, I remember his write-up and wanted to extend his research to see if there's any issues in this library. Although I did not find any, I believe a quick sharing on what encoded strings are can still be useful when testing email address parsing in applications. This is because developers may not be aware that the email parsing libraries they are using likely allows and parses encoded strings. Okay, so if you are not already aware like I was, email address can contain encoded strings, mainly due to email protocols needing a way to transport non-ASCII characters. This is defined in RFC 2047, which is supported by Jakarta Mail. Encoded strings are basically wrapped in the equal and the question mark symbols and consist of three distinct sections separated by a question mark. The first section specifies the char sets. UTF-8 is a commonly supported one. Next up is the encoding, which is either B for base 64 or Q for quoted strings. And finally, there's the encoded text, which is where the payload goes. So we use this example email address that is RFC compliant and deconstruct them into the different components. And this is how it looks like. And so what can we do with such an email address? Well, in Garrett's research, one misuse scenario was he was able to inject an encoded null byte to terminate the email address early. Think of it as being similar to like a null byte injection in PHP strings. So this led to a differential between what is saved as a user's email address by the application and the email address where the emails are actually being sent to. Keep this in mind as we'll look into this differential later. Yeah, so that's a quick primer on encoded email strings. And with all the background information covered, we can now move on to the primitives that I found in Jakarta Mail. And the focus shall be on internet address and the myMessage classes, which are shipped by default. So how I found the primitives was quite interesting, as it was just another day of reviewing our customers' applications. Then I saw references to the native Jakarta Mail's internet address class. I decided to take a look at the constructor to see how the input address is actually being passed. I've noted that there were multiple constructors for the internet address class intended for these different scenarios. And here's one of it for the single string argument. And the intention is to take in an email address and pass it to the pass method, which validates the emails for address for RFC compliance. Afterwards, the email and personal name will be assigned to the object itself. Then there are other constructors here, and there's two more that takes in 2 and 3 strings arguments respectively. Do you notice anything interesting here? If we look at what the code is doing or even the comments, we can immediately see that these constructors are straight up using the input without even calling the pass method. So it is interesting that the single argument constructor actually calls the pass method to check for RFC compliance. But when it comes to this multiple arguments constructor, it doesn't even perform the same checks. It may be an intentional design for some reason, such as features, but the fact remains that this inconsistent behavior between the different constructors can certainly catch developers off guard. Just to do a sanity check, I went to test it out, and I just basically attempted to initialize an internet address object with an invalid string. And yeah, only the single argument constructor throws an exception. So this kind of behavior can definitely catch people off guard. And that's the first primitive from this class. And we can move on to the next one. If we look at the pass method next, we can see how it can cause confusion when passing complex email addresses. In this implementation, this method takes in a single string and attempts to pass it according to RFC 822. We'll use this string here as an example. There's an email address wrapped in angle brackets, followed by another email address. So how do you think this is going to be passed? Well, it seems that only the portion in the angle brackets was extracted as the actual email address. So you might be wondering what is the implication of this behavior. Let's assume this scenario. Say there's an application that identifies its users via their email addresses, and it also grants special privileges to accounts from the foo.com domain. And if the registration is not restrictive enough, we could register with an email address similar to the example we have seen earlier. Note that the string now ends with @foo.com. So we also know that from the example earlier that the email will be sent to the address in the angle brackets. So let this be our attacker controlled email address. And so when the application is granting special privileges, we assume that it also does a simple match by looking for the last index of the @ symbol and uses the remaining of the string. So this happens more often than you think. And it also trusts that the internet address constructor ensures that the input is a valid email string. So the developer may not be aware that the input we have here is a valid email string. This means we can now register accounts with these special privileges granted to the full domain while verifying it through our example.com domain. And this simple example demonstrates how an expectation mismatch between developers and email address parsers can actually lead to high-impact vulnerabilities in applications. From the parser's perspective, it is simply passing the input according to RSC standards. Something else to think about is that this concept is not just restricted to web applications, but also other types of services that rely on passing email addresses to establish identities. Well, what about encoded email addresses? This was where I tried to apply Garrett's research and see if null bytes or any other special characters could break the parser. Unfortunately, the getAddress method in the internet address does not perform any form of decoding on the email address component, so we can't apply any encoding tricks here. Before we move on to the next method, I would like to draw your attention to the comments for the parse method. It says that it is an ad hoc mess and it is not a perfect parser. So let's take a look. And if we look into the source code itself, it goes on for around 450 lines of code in a single method of basically positional checks, very intensive. If you're motivated to look into the exact implementation, I wouldn't be too surprised if you can find some issues here. Okay, another method from the internet address class is the getGroup. So this method attempts to return an array of internet address from the current group address. You might be wondering what is a group address. It's basically a special string that has the following syntax. So you start with a group name and then a colon. After the colon is 0 or more email addresses, with comma being a delimiter, and the entire sequence is terminated with a semicolon. So a group address is different from mailing list address, which we might think of when thinking of a group of email addresses. And so a group address will actually pass the passing of the internet address constructor itself. And if we run the getAddress method to retrieve the pass email, we see that it simply returns it as it is. At least now we know that a group address is valid RFC 822 syntax and would pass this validation. One example of misusing this primitive could be, for example, application that uses a dangerous regex and that's vulnerable to denial of service. So somehow supplying a group address may cause catastrophic backtracking. That's just one example. And now we'll look at the other class from Jakarta Mail, which is MyMessage. And this class is used to represent the message envelope, which includes the email headers and body. What's interesting here is that when passing certain email headers, such as from, reply to, and subject, it will call the internet address pass header method to process them. Then the pass header method will call the same pass method that we just saw. This means that primitives applicable to internet address are also valid through the MyMessage class. These are the MyMessage constructors that take in an email envelope as input and then passes the from, reply to, and subject headers via the internet address pass method. If you happen to come across applications calling any of these MyMessage constructors with user-supplied email envelopes, be sure to take a closer look at how it uses the input from these headers. So we use this sample email envelope here, and we try to pass it using the MyMessage constructor. We are using encoded strings here to demonstrate that values in these headers are automatically decoded by the MyMessage class. This is just some sample code used to pass the email envelope, and that calls the constructor and pass the envelope as an input stream. Anyway, so this was the constructor I used to, the code I used to call the constructor to pass the email envelope as input stream. And if we look at it, we can confirm that the encoded values that we supplied were actually decoded by the constructor. So a potential misuse scenario here is maybe an application that accepts an email envelope file, and maybe it runs an input filter to strip any deny listed words from this input. To bypass this check, an attacker could simply supply encoded strings as part of the deny listed words instead. And when the application calls the constructor to create the email object, the encoded strings are automatically decoded. And in this scenario, so we saw that if an application is unaware that the myMessage constructor actually performs input processing, in particular, decoding encoded strings, it can potentially subvert the input validation logic. Okay, so we are still at myMessage class. The other interesting method is the getRecipients method. So this method receives a header value from the email envelope according to the argument type. There are 4 acceptable types which are defined as a Java enum. The interesting one that I would like to point attention to is newsgroups. So observe that if the recipient type is newsgroups, the getHeader method will be called to retrieve the values from this newsgroups header. The getHeader method then concatenates any duplicate headers with a delimiter, which is common in this case. What this means is that the method actually accepts duplicated newsgroups headers, and this edge case may not be obvious to developers. Let's take a look at how the concatenated value is being passed. In the pass method, it basically splits the input string by commas and inserts them into an array list of news address objects. And the issue can be found in the news address constructor. And observe that the code does not perform any validation except to strip white spaces. Also seen in the comments were that it does not throw an exception if a malformed input is received. So this behavior is kind of different from how the internet address constructor behaves, where an exception is thrown if an invalid input is received. The exact implication of this will depend on how application uses these newsgroup header values. Having duplicate headers may also cause potential issues if developers do not handle them well. So let's take a look at this in action. So here's an email with multiple newsgroup headers. When passed with the myMessage, the result is a list of newsgroup address with spaces stripped. Yeah, so that concludes the primitives in the internet address and myMessage classes. We'll take a look at a couple of classes from Spring Framework next, and they all utilize the Jakarta mail library in one way or another. The package that we are looking at is the org.springframework.mail and its subpackage Java Mail, which contains support for Spring's mail infrastructure. We'll be looking at these 4 classes shown here, which are all found in the Java mail package except for sample mail message. The internet address editor class is used to prepare an internet address object using a supplied email address. If we look at the source, we can confirm that it simply passes the input string to the internet address constructor. So this is another example code which calls the method. And since the input goes directly into the internet address constructor, the personal name field will be decoded if it's an encoded string. As we have seen earlier, the encoded email address are not decoded via the constructor, and only the personal name section will be decoded. Nonetheless, a potential misuse would be phishing attacks. If an application shows the personal name section of an email address first, we can make it look like the email came from a legitimate sender. As for the 3 remaining classes, we can take a look at them together as they are all related. These are the myMailMessage and its helper implementation, as well as the simple mail message classes. They are all implementations of the mail message interface. So the simple mail message class has a similar primitive to the internet address editor that we just saw. The address fields will all eventually make its way into the internet address pass method. And this will decode any encoded strings in the personal name field, which once again may catch developers off guard. And the sample code used to confirm the behavior, basically using an encoded email string here, and verifying that the decoding occurs with the personal name section of the input address. So up next is the myMail message, which is just an abstract class that represents the email object. The helper class is the one used for handling any logic, and the helper constructor takes in a myMessage object as well as a string, which can be sketchy if it's used unsafely. The string in this constructor represents the encoding type of an encoded email string. The constructor will create an encoded string for us if the personal name section contains at least one non-ASCII character using the encoding that was specified. Once again, an implication will be spoofing, as depending on how the application is coded, it may display the decoded personal name instead. I'm not sure how much time we have left, but we can look at one primitive I found in the Hibernate validator library. So the Hibernate validator library uses this email annotation that developers can use to validate email addresses. Unfortunately for us, the default regex in use does not approve of encoded strings. However, it also allows custom regex to be supplied for developers wanting to take matters into their own hands. The default regex is pretty intense, and it performs validations in two parts, before and after the @ symbol. I've played around with the regex to see what kind of strings you could pass the validation, and managed to find one instance. So the string you see here is one that will pass the regex checks. So simply wrap any bad characters in quotes before the @ symbol, and it will likely succeed. And its usefulness will depend on how the application you're looking at uses this email string. For example, if it does a naive split by the @ symbol and uses index1 as the domain, then it may potentially lead to some issues. All right, that concludes the sharing we have today. To recap, we have seen a few primitives from Jakarta Mail Library as well as in Spring Framework. The main takeaway I hope everyone has is that we should always take a close look into the libraries that we use or come across, especially if they have potential to have interesting behaviors like we have seen. With that, we have come to the end of the sharing. Thank you for your kind attention throughout, and I hope you found it informative.